This is Miss Downey continuing with the second part of Chapter 6, Section 2. We're now on Problem 2. So now we want to simplify a radical expression. It says, what is the simplest form of the cube root of 54x to the fifth power? So again, we're going to apply these concepts we just learned. And the first thing we want to do is find all the perfect cube factors. So we have 3 cubed, which would be 27. Oops. So 3 cubed, 3 times 3 times 3 is 27. And then times 2. So 27 times 2 is 54. So we found a cube factor of 54 being 3 cubed. Now we want to split our x fifth up to an x with a cubed. So there's our x cubed, and that leaves us with the x squared. So now that we've found all of our perfect cube factors, now let's regroup, and that we want to group our cubes together. So here's our cubes, the 3 cubed and the x cubed. And then the leftovers, the 2x squared there, using our new property. And then we want to clear this out now, simplify that to 3x. And then we're left with the cube root of 2x squared. So that is our final answer. 3x times the cubed root of 2x squared. I like to think of this as when you have this index and then your powers match the index, they sort of cancel each other out. And when you can clear all those, you take away your radical sign, and that just leaves you with the 3x. It says, how do you know when you're done simplifying? Well, you're done when the radicand contains no perfect cube factors, or whatever your index is. In this case, it was cube. Here's our got it for more practice. And pause the video if you'd like to work it. So in problem 2, it involves simplifying a cube root. So the absolute value symbols were not needed because it was cube, it was odd. We only put them on the even. So remember to combine the nth power of a, nth root of a and the nth root of b by multiplication. And both radical expressions must be real numbers. So let's look at problem 3. Simplifying a product, we're still multiplying. What is the simplest form of the square root of 72 x cubed y squared times the square root of 10 xy cubed? So we've got our thinking right here. So you need to multiply the radicands to find the perfect square factors. So you think about what you have here. Because they're both squares, we can combine them. He's a square root, he's a square root, so we can combine it into one statement here. And now you want to do the math. So you have the 72 times 10, which is 720, and the x cubed times x. Well, you just add the powers, right? Because it's like x to the 1. X to the 3 times x to the 1 is x to the 4th. And then y2 times y3, you keep the base and add the powers. So it becomes y to the 5th. So now that we've combined these, now we've got to pull it apart with a perfect square factor of 720. And we know that 144 is a factor of 720. And 12 squared is 144. So we can rewrite 720 as a product of 12 squared times 5. And then we want to take the squares out of our x's and y's. So we have x squared squared and y squared squared times y. So now we want to put all of our squares together. So we've got our 12 squared, x squared squared, and our y squared squared. And we're just left with our 5y. So the 5y goes over here, and all the squares come over here. Now that we have all of these squared, we can remove the squares and clear the radical. And it leaves us with our radicand. 12 times the absolute value of x squared y squared. And because they are squared, that's an even, so it's going to have the absolute value, times the square root of 5y. Now, because these are squares, there's no way we will ever have a negative sign in these. They're even powers. So we can take the absolute value signs off, and it leaves us with 12 x squared y squared times the square root of 5y. So that is our simplest form. Here's our got it for problem 3. If you'd like more practice, pause, work the problem, and come back. Okay, so now we're back, and we're going to work on multiplying, which we did in the beginning, and dividing. So now we're going to work with division of radicals. So since we define division in terms of multiplication, we can extend this property for multiplying radical expressions. So on the left is the multiplying that we discussed earlier, and on the right is our dividing. And now, if the indexes are the same, we can write a quotient of roots as a root of a quotient. So here we have the radical 2 over radical 3. We can rewrite that as 1 radical, or square root of 2 over 3. And here, likewise, we've got the cubed root of 4 over, or divided by, the cubed root of 5. And we can rewrite that as 1 cube root of 4 over 5. And that's all that is. So here's the property of combining. You may pause and write this if needed.